Well, look, you can cut me at any point if I am taking too long, okay? Because I'm very bad with the online presentation. So if you see I'm extending,
Okay,
let
okay.
me know. You have a couple of minutes more, and then I close. Not
Okay, good. So
necessary
welcome
to go
everyone.
all over the details.
Yeah. Okay, no worries. Welcome everyone. We have the pleasure this week to host Adolfo Cisterna, who got his PhD in Valparaiso in 2014. And since then, he's been traveling around. He was in Valdivia, if I remember correctly, Trento, and for a couple of years now, he's been in Prague, in Charles University. And today, he's going to talk about stationary and axisymmetric spacetimes in Einstein-scalar theories. So, Adolfo, the floor is yours.
Okay, thank you very much for this kind invitation. Please, if you want to ask something, stop me at any point. We can discuss. So yeah, I'm gonna talk about these two works that you can see here, the archive. They are both papers already published that are related with mostly results we got in GR, so just in pure general relativity with some scalar fields going around in some of these results, but not too many. Most of what I'm going to talk today is going to be GR, and at the end of the day, we'll try to say a few things with Einstein-scalar theory. So basically, we have been working a lot during the recent times on constructing new stationary and axisymmetric spacetimes in GR using Lie point symmetries, which are some symmetries that are hidden in the Einstein-Maxwell equations when they are formulated in this Ernst fashion that I'm going to introduce you today. So before starting directly with what we did in those papers, first, let me motivate you a little bit about why we should study exact solutions. Well, I didn't say, but all of these solutions are going to be exact. So there are no numerical results here, basically because we don't know numeric. So we prefer to actually work with exact solutions. But many people at some point, they're asking you sometimes, especially when you do modified gravity, okay, but why all this urge to look for exact solutions? So let me motivate a little bit that. So we can always say that given any physical theory, actually exact solutions are very useful and they play an important role. Very trivial examples are Maxwell theory. We know that there are Coulomb fields, dipole solenoids, and so on that actually provide us with an interesting toolkit to deep into the study of electromagnetism. In quantum mechanics, it happens something similar because you have Schrodinger equation, which is also linear as Maxwell equations, and studying very simple solutions of Schrodinger equations, like the harmonic oscillator, several potential wells, and so on, or 3D problems, like the hydrogen atom, provide you with glances on very fundamental concept of the quantum world, like the quantization of energy, the degenerate states, minimum energy state, and so on. And when you go to nonlinear theories, as for example, when you combine Newtonian gravity and fluids to try to describe some astrophysical objects, and everything becomes more loose linearity, let's say, it becomes nonlinear, then having exact solution is even more important because actually to get intuition about nonlinear systems is much more difficult. And in addition, on top of that, we can say that actually, although numerical computations are very relevant to study highly complex systems, like, for example, the merging of binaries and things that are really relevant from an astrophysical point of view, to have certain type of exact solution actually works as a map road, right? To follow when applying numeric. And an example of this is the Kerr solution, right? Which is the most important exact solution we have at hand from a astrophysical point of view. And actually, many computations that are done in astrophysics when colliding stars or whatever are based a little bit on the Kerr metric. So many people are working actually on modifications of the Kerr metric in order to describe more relevant astrophysical situations, more complex ones. And without having Kerr, which is an exact solution that took a lot of time to be found, this will be very difficult. So it's important to have exact solutions at hand in any gravity theory we are looking at. Now we are dealing, as I told you, we were mostly working in GR, so we will be dealing with Einstein equations. And even though it's in terms of fields and field equations, it's the simplest of the theory, Einstein equations are already very complex. They are given by a complex set of nonlinear coupled PDEs. And when you are solving these equations, you have two challenges to face. So one of them is is a mathematical challenge, which is to find as many solutions as there are in your field equations, or to find a solution as general as possible. And then once you have faced the mathematical challenge, you have the physical challenge, which is to go beyond the local solution of the PDEs and to understand the spacetime from a global point of view. Because usually when we are looking for exact solutions, we are in a particular set of coordinates. It's a very local tool. And sometimes because you are working with a particular set of coordinates, there are some undesired features of your solution or things that you cannot understand because of the bad choice of coordinates. So it's important to have tools that allow us to understand globally the spacetime, for example, algebraic classification and so on. So these are basically the two main challenges that solving Einstein equations propose. To find general solutions in exact solutions already in GR is therefore very complicated, but how do we do this? Well, usually you can apply brute force and try to integrate solutions. You might be able to do this in a spherical symmetry sometimes, always static solutions, and it's the case of Schwarzschild, radial, from very simple exact space-time. Even in modified gravity, you can do this usually when you are under spherical symmetry or with exact gravitational waves that usually solve equations in a very universal way, like PP waves, ideas waves, etc. But in general, it's difficult. If you go and you turn on stationarity and you go for rotating solutions, to find exact solutions is very complicated. So usually you need to use solution generation technique that are very often based on Lie point symmetries. Okay? And to hit the physical challenge, usually what you do is that you understand the algebraic classification of the spacetime. You understand what type of spacetime is the one you are dealing with, and then you can understand the nature of the Weiss tensor, and knowing this, you know the type of gravitational field you have at hand, a gravitational field with a Coulomb behavior, or that has a gravitational wave, and so on. But what are these Lie point symmetries? That are the things that we are going to use. Well, these are like local group of transformations that map every solution of the system into another. So there are symmetries of your system of PDEs that allows you to map in between, like it's a map inside of the spectrum of solutions you have. So basically, when you detect Lie point symmetries of your field equations, you can move from one solution to another within the same system. And this is very nice because usually the techniques we have to find solutions knowing a known solution, a seed, something we call the seed, are usually frame transformations that move you from one theory to another. Something we are gonna see in a few slides, right? But Lie point symmetries keep you within the same theory. And although it might appear straightforward, like, okay, I found a Lie point symmetry, so I have a sort of algorithm to find solutions. Actually, it's not that easy. It's not that simply to, it's not like that systematic, because first of all, it's very difficult to discover them. And second of all, once you have Lie point symmetry at hand, you need to assess the applicability properly, because you don't know actually, in general, in many cases, you don't know which is going to be the effect of applying the transformation, and it might be that this Lie point symmetry you are using is giving you nothing else than the same solution within different coordinates, and it's basically a different gauge of the same solution. So this is important to actually accurately recognize the applicability of these Lie point symmetries. So let me tell you a bit about the outline of this talk. So I'm going to say a few things about stationary and axisymmetric spacetime, in particular the circular subset. I think all of you know this very well, so I will try to go fast, but there are some details. Then I'm going to show you Einstein equations in the very general case of stationarity axisymmetry and of stationarity and axisymmetry, and again in the circular subset. And I will tell you what the Ernst scheme is and what are the Lie point symmetries associated with this particular way of writing Einstein equations. Then I'm going to tell you a bit about the static case that is contained in this family of metric. It's something that's called the Weil problem. I will show you why this Weil problem is very important to understand it, especially when we are looking with solutions in Einstein-scalar theory. We will see that there is a connection in between Weil metrics and space-times that are supplemented with a minimally coupled curve. And two important examples to understand the logic behind solving the Weil problem are the Schwarzschild metric and a metric that is called the Zipoy-Voorhees space-time, which is a generalization of Schwarzschild with multiple with multiple terms. Okay, it's like an axisymmetric generalization of Schwarzschild. Having this at hand, having understood how it works the Weyl problem, then I will tell you the extension of this problem to the case of Einstein-scalar theory, and I will show you a theorem, which is called the Eriş-Gürses theorem, that recently was somehow analyzed by us and other groups tangentially, that allows you to always take a solution in GR, no matter how complex it is, even in the general stationary and axisymmetric case, and dress this solution with a minimally coupled scalar, okay? And at the end, I will show you a few examples. So I will put a scalar field all over Kerr. This was known before. I mean, other people did with a different method, but Kerr with a scalar field was known. But we did in a way that the computational cost was lower somehow. And for the first time, we applied this in 5 dimensions, and we were able to put a scalar field over flying, let's say, back reacting. Now, it's not like a test scalar field. This is always back reacting on a Meyer-Sperry spacetime, actually, with both angular momentums completely arbitrary. Okay, and this is an indication that actually there is an extension of Gürses theorem in dimension 5, although we are now writing the theorem and we didn't put in these references, but it's like that. So what is stationarity? You all know that the stationarity is basically when your metric do not depend on time, although there is some degree of movement, right? Things that rotate, for example, the metric components, they do not depend on time, but actually you have some sort of movement going on, which is the rotation of the spacetime. But more technically, you can say that you have a spacetime, which is I'm calling M, that is endowed with a metric G, and it's going to be stationary if there is a group which is isomorphic to what you see here, to the R plus, which is the group of unidimensional translation, and of which the orbits are time-like curves on M. And basically, the metric is stationary if it's invariant under the action of this group. So basically, the Lie point derivative with respect to the generator of this group is equal to 0. And usually, the parameter associated with this group of unidimensional translation is called T in a very suggestive way, right? Usually what you can do is that you can uniquely determine this generator by demanding that its norm at infinity is -1, and so T coincide with the proper time of an asymptotic inertial observer that is at rest with respect to the object, with the stationary object. Now, I might say that this condition is not always satisfied on every spacetime, because sometimes we have ergo spheres. The ergo spheres go all the way to infinity, so it's more tricky to define this uniquely, okay? And stationary spacetime, they have a subset of spacetime, which are called static, and that basically are all stationary spacetimes in which this generator of the symmetry is orthogonal to a family of hypersurfaces. And how do you make sure that this is the case? Well, you use Frobenius theorem, the integrability condition of Frobenius theorem, and if it's satisfied, it means that this scaling vector is tangent to these hypersurfaces, and then you say that your spacetime is static. And intuitively, we can say, okay, the spacetime does not depend on time at all, but also nothing is moving. So this is the difference with stationarity, in which things do not depend on time, but actually there is some degree of movement, which is the rotation. And actually, from this condition of Frobenius, you can prove that if it is satisfied, the twist tensor of your spacetime must vanish also, and this implies that there is no rotation. So a static spacetime, they do not rotate at all. And in very simple terms, you can say that usually that the metric representing a static spacetime must be diagonal. On the other hand, you have axisymmetry, and then it's the same story, but now there is another group which is homomorphic to SO2, which is the group of rotations in the plane. And then you say that the metric is invariant under this group of rotations, being K, the generator, associated with some parameter we are going to call phi. You can uniquely determine the scaling vector also by asking that phi has a period over 2π, and so on. And stationary and axisymmetric spacetimes are actually spacetimes that are invariant under both symmetries. So basically, your spacetime Mg is invariant under the action of this abelian group R times O2. And usually, we can see that there is no loss of, it was proven, I think, by Carter that you don't lose generality if the action of this of the stationarity and the axisymmetry are considered as commutative. And this is very important because if they are commutative, this implies that you can consider your parameters defining the group of stationarity and the group of axisymmetry as coordinates on your spacetime. This allows you to write a system of coordinates that will be adapted to these two symmetries we are asking the spacetime to have. So basically, when you do this, you can write always a chart on your spacetime that is gonna be given, let's say, by the Killing coordinates t and phi, but another couple of coordinates, non-Killing in this case, r theta, or if you are in cylindrical coordinates, rho and zeta. And then when you are already in these adapted coordinates, everything simplified, and your Killing vectors are simply this base you see here that we always know, and the condition of the metric being invariant under the generator by using the Lie derivative simply reduced to the condition of those coordinates being ignorable, right? So the derivatives of the metric components with respect to t and phi are 0. But by imposing this stationarity and this axisymmetry, still we are dealing with a very general spacetime in which many unknown components need to be integrated when dealing with Einstein equations. And there is a nice subsector of these spacetimes that are called circular spacetimes that allows us to actually simplify much more the line element of something that rotates and that do not depend on time, okay? And fortunately, in GR with very useful type of fluids and with Maxwell fields that also follows staticity and axisymmetry, all solutions are always circular. This is a theorem, the circularity theorem. So most of the time we are dealing with that. But when we are dealing with theories like in modified gravity, when you have a scalar field, or more probably astrophysically relevant type of fluids, then circularity is not for granted, shouldn't be taken for granted, and then you need to deal with more general spacetimes. But let us see what this circularity means in a very generic way. So when you have stationarity and axisymmetry, there are some privileged two surfaces in the spacetime, and these are, of course, the orbits of the action of the group, right, of RS2. Sorry, R times SO2. And these orbits of this group action are called surface of transitivity, that here I'm calling PA, piece of A. So when you are in adapted coordinates, these transitivity coordinates can be always labeled by the remaining coordinates r theta, where this is going to be the label. It doesn't imply that they depend on r and theta, because remember that they are the ones defined by the coordinates t and phi. And in particular, these circular spacetimes are a spacetime in which you are asking this surface of transitivity to be always orthogonal to another family of hypersurfaces that now are determined by the other remaining coordinates, in this case, r and theta, okay? And these are called meridional surfaces. Spacetimes in which you can always do this, and a spacetime in which you can take your surface of transitivity and find them to be orthogonal to these meridional surfaces are called circular spacetimes. And when you do this, in the process of finding or defining a spacetime that will satisfy this property, many of other components of a general and non-circular stationary and axisymmetric spacetime are going to be vanishing. And because of that, because of asking the existence of these meridional surfaces that are going to be always orthogonal to the surface of transitivity, these components can be made to vanish and reduce much more the line element with which you will be working. When this is the case, we say that the action of this group, R times SO2, is orthogonally transitive, and that this spacetime is circular. So by taking a general line element, asking for stationarity, and asking for axisymmetry, and asking for circularity, then you can always write your spacetime in this form you see here, okay? There are other details that you can read there, but this is the most important part. So basically, you arrive to something that is known modulo using Einstein equations, because you use Einstein equation to reduce the amount of free functions you have and so on. And what you get, what you arrive is to the so-called Weyl-Levis-Papapetrou line element. And the Weyl-Levis-Papapetrou line element is the most general spacetime you can have that respect stationarity, axisymmetry, and circularity. I wrote it here in coordinates rho and theta for the non-killing ones, because this cylindrical symmetry somehow is going to be very useful for us when dealing with the Einstein-Maxwell equations written in the Ernst fashion. Okay, but in principle, rho and theta can be any other pair of non-killing coordinates. It might be a spherical like r and theta or whatever. Okay. So yeah, this is interesting because there is a theorem, this Papapetrou theorem, that will tell you anytime that your T mu satisfy these two conditions, that your spacetime it will help you to determine if your spacetime is circular or not. As I already say, in vacuum they are always circular. If T mu is for example, a perfect fluid, or you are in vacuum, or you have Maxwell fields that satisfy the same symmetries that the Weyl-Levis-Papapetrou answer. Okay. So let us deal now with Einstein equations in a Weyl-Levis-Papapetrou line element, in this very general answer you see there. So F, of course, is your lab function. Omega is the function of the dragging of the spacetime induced by rotation. And gamma is a function that determines this conformal factor on top of the non-killing sector of the metric. If you use this answer into Einstein equations, you get to this very complex system of equations that relates the function f with rotation, and that give you the non-killing part of the metrics always in terms of f and omega in sort of quadratures that in principle you should be able to integrate. But to find solutions first, these main equations, the ones that you see in blue, is very difficult. If you go straightforwardly there and you're trying to find any non-trivial spacetime like Kerr, for example, and so on, is very difficult. We know that to find Kerr, some very sophisticated techniques were invented back then. Like people realized the existence of several theorems regarding the classification of spacetime and so on. This allowed them to write Kerr. Now we understand that Kerr can actually be integrated in a Kerr-Scheil fashion with much more simplicity than just going straight forward and trying to solve these equations. But in general, to deal with them is difficult, and there is a very nice scheme that allows you to simplify a lot of the computations to find new solution, and that at the same time provides you with a set of symmetries that when looking at this equation in this fashion, you don't see, that are like somehow hidden, but that are disclosed when you move to this new formalism, which is called the Ernst formalism. Well, not new, but this other way of writing Einstein-Maxwell relation, because actually Ernst formalism is from the 60s or 70s. So let me introduce you to what the Ernst scheme is. So basically what I'm going to say now is simply a way to rewrite these sets of equations you see here in blue and in red, okay? And we will see that when having the equations written in that way, things simplify a little bit, and that also this set of Lie point symmetries that I told you I'm going to use are going to be disclosed. So what is this Ernst scheme? So basically, Ernst has shown that for the spacetimes that are, again, stationary, axisymmetric, and also circular, because it's also unique circularity, the solutions of, the field equations of Einstein-Maxwell equations can be reduced to this couple of nonlinear complex vectorial equations you see here, where this capital epsilon and capital phi are two functions that I'm defining here, and that are defined in terms of the metric function and the gauge field of my original Levis-Papapetrou configuration. So let me go back a little bit. So keep in mind that we have a Weyl-Levis-Papapetrou answer of this form with f, omega, and gamma, and that I will be taking a general gauge field, but that respect the same symmetries, which will have an electric component that I'm calling AT, and a azimuthal component I5, okay? Earth have shown that you can rewrite this system of equations I showed you before in this manner I am showing you now, where you define these two complex potentials, epsilon, which is a complex potential of gravitational origin, so it deals with gravity, and this complex potential phi, capital Phi, which deals with the electromagnetic configuration, okay? And you see here two extra pieces of this potential that do not appear in the original Weyl-Barbeto configuration, which are called chi and I bar phi, that are called the twist potentials, and that are found using two integrability conditions that arise when writing Einstein equations in this formalism, which are the so-called twist equations. So basically, the complex part of each of these potential is some function that needs to be found via these twist vectorial equations. Which is the nice part? The nice part is that all these vectorial quantities that you see here in this equation, so, sorry, we have to, okay. All these vectorial operators you see here, the divergences, the Laplacian, and all of these curves, they are defined on a space-time with cylindrical symmetry, in a flat space-time with cylindrical symmetry. So this is nice because you somehow decouple time from your field equations due to the symmetries of your space-time, and you projected Einstein-Maxwell equations of this four-dimensional curved space-time into a three-dimensional space-time, which is given in cylindrical coordinates. You might ask, okay, but there is one remaining function of the original Weyl-Barbeto answer, which is gamma, that do not appear in this scheme, and do not appear because gamma is still given by a couple of quadratures in terms of epsilon and phi. So basically, every time I solve these equations, I will always know what gamma is. Okay? And how do I go from the Earth formalist to the metric formalist? Well, very simple. If I am dealing with Earth's equation and I am solving directly these equations here, what I do is that then from the form of my complex potentials, I read off back the form of my function f, the form of my gauge potential, and via the twist equations, I find what omega, which is the rotation, and what I phi, which is the magnetic field, are. This is one way to deal with this, okay? Now, which is the main property of this formalism? It's not actually dealing with solving these equations. Although, for example, Kerr solution is a very simple linear potential in the coordinates for epsilon, and Schwarzschild is trivial here, and many other solutions are super easy. The form of the potential is extremely easy when working with particular coordinates. The main use you can find of this scheme is that these equations, the Earth equation, which are nothing else than Einstein-Maxwell equations written in a more sophisticated manner, they are invariant under a set of Lie point symmetries that I display here. The first is a gauge symmetry. It's nothing else than gravitational gauge symmetry. So basically, I am taking my gravitational Earth potential and I am changing it. I'm changing it by its complex part by a constant. This will produce nothing else than a change of coordinates, because if you see here, the complex part is given by this chi. So basically, I'm modifying chi. But if chi is a constant, there is not going to be any back reaction on the form of the rotation, because this guy is a constant. So I'm not introducing rotation, not introducing anything. I am simply modifying by a gauge the gravitational potential. Then we have this second transformation that I call T2 alpha, which is another gauge transformation, but of electromagnetic origin. So basically, I'm changing my initial gauge field configuration by a constant. Then, of course, we have a Weyl rescaling of the metric that is supplemented by a duality rotation on my gauge field. So basically, this is the electromagnetic invariance under duality rotation of electromagnetism. So something known for Maxwell and equal 4. But then you have two non-trivial Lipoin symmetries that are called the Ehlers transformation, that it depends on a real parameter that I'm calling C, and we have the so-called Harrison transformation that depends on a complex parameter that I'm calling beta here. And these two, they have very non-trivial effects. So let me tell you what they do, as to be direct to the point. So basically, if you take your initial seed potential, this might be Minkowski, any solution of the entire spectrum of stationary axisymmetric circular solutions. If I apply this transformation, if I take the seed potential and I divide it by this thing you see here, and you do the same with your gauge field, what happens to your space-time is that in one case, it might acquire NUT parameter. So it might take a solution and induce a NUT parameter. I guess you know what the NUT parameter is, but it's a stationary, it's the first stationary generalization of Schwarzschild. It's not Kerr-like rotation, it's not type of rotation, it's something different, but this is what it does, the Ehlers transformation. And it also can have the nice effect of producing what is called swirling. Swirling is a rotating background. So you have a space-time that has some sort of vorticity and that rotates, but it's not rotating because there is a source on top that rotates and that drags the space-time. It's actually the other way around. There is a background that rotates that is taking with itself the body I put on top. Okay, this is the swirling rotation. And then Harrison transformation has the nice effect that takes a vacuum solution. Well, it can be electrovacuum, of course, but it takes a vacuum solution and put it into an electrovacuum one. Yeah, sorry, I have a typo here, but this is like this guy, this numerator should be here, and here should be only beta epsilon 0. Okay, so please take into account that this beta epsilon 0 plus phi 0 should be here. Why? Because then you will see that you might have no electromagnetic field phi 0. You have a non-trivial transformation for your gravitational potential, but because of this beta epsilon 0 going on here, you will induce anyway a non-trivial gauge field. So this transformation has the capability of taking something that is a vacuum solution and transforming it into an electrovacuum solution. And what it does in concrete terms is that it can take a given solution and endorse to it monopolic electromagnetic charges, electric and magnetic charges, or can take a space-time and can distribute a background electromagnetic field on top. This is called the Melvin-Bonner universe. Now you might be asking, okay, but why, under which circumstances, the same transformation produce two different effects? Well, this is a very good question, but I didn't tell you, I should have before, but if you see here, I said this is Levy's Weil-Papapetrou, and I put a subscript E and M, and this means electric and magnetic, and the difference between these two line elements is that in the original Weil-Papapetrou element that I told you was the only one that was the most general stationary, axisymmetric, and circular, well, it's not the only one, there is another one, which is the magnetic version of this very same line element that is obtained via a double weak rotation between the killing coordinates. So I say T is going to be the imaginary unit times phi, and phi is going to be the imaginary unit times T. When you do that, this minus here disappear. This becomes d phi, this becomes dt, and here you get minus dt squared. This is known as the magnetic bi-level spacetime. Okay, it's just a normal bi-level spacetime as the one you see here, on which you have applied the discrete double weak rotation transformation. The funny thing is that this is also stationary, axisymmetric, and circular, and do not modify the shape of Ernst equations. The only thing that it modified, I didn't put it just because there was no need to overcharge the notation, is that we'll modify a little bit these expressions and we'll change the Twist equations, but they are known. So every time you are dealing with any of these Lipon symmetries, you might decide, okay, I would like them to be acting either on the electric Weil-Papavetru spacetime or on its magnetic version. And depending on which you are using, you get any of this effect. For example, Ehlers in the electric one introduce NUT parameter, but Ehlers on the magnetic one deals with the swirling universe. Harrison in the electric provides electromagnetic charges, monopolic ones, and Harrison in the magnetic one produce background electromagnetic fields. And this is closely related with the fact that when you do the double weak rotation on this spacetime, you change the asymptotic of the spacetime. They are not asymptotically flat anymore. Well, another thing I should say is that all of these Lipon symmetries are valid in Einstein-Maxwell. They don't accept the inclusion of a cosmological constant. So we are dealing with asymptotically flat solutions. When you when you do the double weak rotation between T and phi, you are changing the asymptotic, okay? And this has an effect on the resulting spacetime after you apply the transformation. And actually, Swirling and Melvin-Bonner, they are a spacetime with a very strange asymptotic. Actually, in terms of spacetime are known, they are asymptotically Levi-Civita spacetime. So these are a spacetime with some degree of cylindrical symmetry. Okay, NUT is locally flat, and of course, Rydell-Nostrom or Kerr-Newman is asymptotically flat. So you might be wondering, okay, but which novel spacetime has been constructed in this way? Well, the most non-trivial ones you can get from here are Swirling and Melvin. Melvin was found initially in the 60s or the 70s by these two people, by Bonner first and then by Melvin. And at least at the level of background, this means I have Minkowski, and I transform Minkowski in a sort of capacitor, electromagnetic capacitor somehow all over the spacetime. That can be integrated by brute force. There is a way to do it without using this technique. But anytime you want to put even Schwarzschild on top and magnetize, somehow electromagnetize something beyond Minkowski, this is automatically too difficult to be done by brute force integration of the field equation. And then you need to use these symmetries. So all sort of Melvin-Bonner spacetimes with any sort of black hole on top, Swirling and combinations thereof, they are found by using this transformation. So for example, one of them is the electromagnetic background. This is in cylindrical coordinates, you can write the Melvin spacetime with a background electromagnetic field. This is written in cylindrical coordinates, and it has this form. If you see, if I kill these two parameters E and B, which are electric and magnetic fields, and there are nothing else that the real and the complex part of this complex, the real and imaginary components of this complex parameter beta, if I kill them, I am basically getting rid of the Harrison transformation I apply on Minkowski, and what I get is Minkowski. Just that Minkowski is gonna, because then this goes to 0, B, this function I defined, it goes to 1, and you get simply Minkowski on cylindrical coordinates, okay? The other spacetime I showed you before is the Swirling one, and this is very nice spacetime because it's a rotating spacetime in which the background is rotated. So if you see, I call J to the parameter transformation of the Euler symmetry I showed you before. Before I call it C, now I'm using J, sorry for that. If I kill J, you have again, there is no rotation here because this is linear on J. And then you get Minkowski in cylindrical coordinates. But once you use an Euler transformation in the magnetic Weil-Papavetru ansatz, the Euler transformation produces this spacetime, which is rotating. You see here the cross term, and it's called the Swirling spacetime. And this is a very interesting type of rotation. It's not like the Kerr one because this is the background. It has many geometrical properties, the way in which it rotates, the aerosphere that produce many things that are completely different than in Kerr. The asymptotic is not asymptotically flat anymore, but asymptotically Levi-Civita, and so on. Recently, we also combined both of them. Well, swirling was known. I think it was known from a paper of Tau, which is one of the authors of the Tau-NUT solution. And it was understood as an analytical continuation of some cosmological spacetime that is inside the family of Tau spacetimes. But then in a paper of Gibbons, Pope and someone else, they were studying the ergosphere of a magnetized Kerr-Newman black hole. So basically you have a magnetic field all over the spacetime and you put a rotating charged black hole. With this technique, you get the metric in closed form. It's a huge expression, but it's manageable. And they understood that there was something like a swirling spacetime there, but they didn't know what it is. And actually, Astorino just 5-6 years ago analyzed this metric in more details, and he found that it was simply the magnetic counterpart of an Ehlers transformation. So basically, it's a sort of magnetic cousin of NUT. And recently, we analyzed and described the geometric properties of mixing both Melvin and swirling in what is called the electromagnetic swirling universe, which is this expression you see here. If you see this line element, there is no black hole at all. It's simply the background, okay? All of these background they have interesting properties, and you can put a black hole on top and so on. So it's interesting also to, in general, analyze what happened when these transformations combine. For example, Ehlers are known to commute. So one Ehlers transformation on top of another is simply another Ehlers in which you have redefined the Euler parameter. So I can apply 10,000 times an Euler transformation and when I get a Euler transformation. They also commute with Harrison. So I can apply an Ehlers and a Harrison, and it's going to be the same that I'm applying Harrison and Ehlers. And on the other hand, Harrisons, they do not commute. So this is tricky because I can apply Harrison on one hand, then another Harrison, and my result, generically speaking, for arbitrary parameters, is going to be the combination of an Ehlers and a Harrison. So basically, it's telling me, look, if I have a solution and I'm going to transform it into an electrovacuum one, I will go from something that maybe has no charge. I'm going to apply twice Harrison to, for example, first include a monopolic electric charge, and after to take that charge and to put it on top of a Melvin universe. I will get that something that will have some degree of stationarity, although the initial spacetime was static. Why? Because the combination of two Harrisons usually includes an Ehlers, and Ehlers either include NUT or swirling. So basically, it's telling you that there is a sort of non-trivial momentum in your electromagnetic field that is producing some rotation, kind of. And this is nice. This is nice. Well, but all of these are things that were known before. What it wasn't explored, and that we did recently, and I'm going to tell you now, is that all of these combination rules, the way Ehlers commute with Harrison, the way Ehlers close as a subgroup of the Lie symmetries, and the way Harrison combined producing stationarity in general terms, all of these things are true when they are applied on the same bilateral Pavlovich ansatz. This means my line element is going to be written, my seed, the seed spacetime in which I'm going to work with, is going to be written either in the electric bilateral Pavlovich ansatz or in the magnetic. But I cannot obtain these rules if I combine the ansatz. What it means? Let's say I take the electric one, I apply a Harrison, and then instead of applying another electric Harrison, I will apply a Harrison, but in a magnetic fashion. Then things completely mess up, nothing commutes, and it's very difficult to know what is going on. And recently, we found that many spacetimes can be found in that way. The only problem is that we didn't find a way to ensure that eventually the generation of a spacetime by consecutively apply all of this transformation eventually close. We don't know that, but we described several backgrounds and stuff that were not known, analyze a little bit the geometry, and so on. Unfortunately, many of these geometries, because of the complexity and all of these parameters interacting, They sometimes feature closed-line-like curves, singularities, and stuff. So yeah, the astrophysical relevance of them is difficult to measure. But let me give you anyway an example. So let's say that I will take Schwarzschild as my seed spacetime. Okay, this is the solution of my Einstein-Maxwell equation that I know, Schwarzschild, with of course no gauge field. So I'm going to apply an electric Harrison transformation. The effect of this electric Harrison transformation will be to, in the case where the parameter beta is real, will be simply to apply, to endorse on my Schwarzschild spacetime magnetic monopole, for example. So I'm going to have magnetic Reissner-Nordström. Okay, this is going to be the effect. Okay, fantastic. And then I'm going to apply on top of that another Harrison, but now of magnetic origin. And this what it's going to do is that it's going to apply, it's going to take my Reissner-Nordström that I got already from the first transformation, and it's going to put it on top of a electromagnetic field. This solution is known, and it's called Reissner-Nordström-Melvin spacetime. And it's known, it has several properties, has been studied in several contexts, and it's nothing else than the Reissner-Nordström spacetime, put it on top of a electromagnetic universe. Depending on what kind of monopolic charge I have and what kind of background electromagnetic fields I have, there is going to be some sort of rotation, because of course the electrodynamic will induce some momentums in the field. So for example, if I have electric monopolic charges and magnetic background, this thing is going to rotate. If I have electric charge and electromagnetic field, most probably there is going to be a conical singularity that will accelerate my spacetime, because I have the acceleration produced by the electric field on the electric charge. So I'm not giving you all of these details because I don't have the particular metric there, but the only point is that when I apply in this direction the transformation, what I get is Reissner-Nordström on top of Melvin. But now let me invert the action and let me take Schwarzschild, and instead of putting an electric charge on Schwarzschild, I will first put Schwarzschild on top of my electromagnetic universe. So then, of course, the first thing I'm going to get is Melvin. It's going to be simply Schwarzschild on a Melvin background. And then I'm going to apply the electromagnetic, the Harrison in the electric fashion. And what I get is something different, because these do not commute. So basically, in the figure you see, I have Melvin, and I'm going to put the black hole on top. So when I apply Reissner-Nordström, first what I did is that I took charge and I put it here, and this stopped being Schwarzschild and started being Reissner-Nordström. And then this one was put on top, this magnetic field, electromagnetic field. But in the other case, what I do is that I take the Schwarzschild and I place it on top of the background, and then I add the monopolic charge. But then the interaction of this monopolic charge with this spacetime is different than with this one. For some reason, which is we have some suspicions about why this is going on. What is the reason behind this is that in the first case, the electric charge gets located on the horizon of the Schwarzschild, right? And this is what it produces the Reissner-Nordström. And then you simply take the Reissner-Nordström and put it on Melvin. But when you already have Schwarzschild on Melvin, the electric charge is not only going to the horizon of the black hole, but it's also interacting, it's getting allocated somehow in the background. And this is why we call this Schwarzschild-Melvin charge spacetime. And they have completely different features and completely different causal structure and so on. So basically, when you combine all of these transformations acting on different Papavetro ansatz, they give different results. You can do the same with swirling, and you can take Schwarzschild, making NUT, put it on swirling, or you can take Schwarzschild, making swirling, and put NUT on top. And they are, again, non-equivalent, okay? So this line, with these spirals, I intend to describe this type of background that rotates. Okay, so this is the story behind these Lie point symmetries, and they are very useful to find new solutions in GR. And they apply to the entire set of stationary axisymmetric circular spacetime. So you can take any solution with these symmetries plus circularity, and they will be subjected to the use of the Lie point symmetries of the Ernst equations, okay? So you can always deal with them. But now I would like to start looking for spacetimes in which I have also a scalar field around. And the first things we need to, the first thing we need to have in mind to do that is the so-called bind problem. So the bind problem is a simplification of what I showed you before. So before we were dealing with the most general stationary axisymmetric circular spacetime. Now let me go to the most general static axisymmetric spacetime, okay? So now I make everything static. So of course there is no rotation. And this static version of the Weil-Leitz-Boisvert answer is usually called the Weil metric. And which is the very nice feature of this simplified case is that when I am in vacuum, so no electromagnetic field as well, so no cosmological constant, no other fields, and no electromagnetic field, only vacuum, no electrovacuum, Einstein equations can be completely solved. That means that mathematically, all solutions are known. Why? Because you can see that taking Einstein equations in vacuum, one of them immediately implies that this function u, that now notice that I change f for exponential of 2 times u, just for the sake of one of the argument. The TT component of Einstein equations tells me that basically the Newtonian potential that describe my line element is given by Laplace equation on a Euclidean three-dimensional space-time in cylindrical coordinates. This is the first thing you get when you go to the static case. This didn't happen in the rotating case, because if you allow me to go back in these equations, where f should be exponential of 2u, if I have rotation, this doesn't happen. If I kill rotation here, and I change to the gauge I showed you before in this metric with exponential, this will reduce to Laplace equation in a Euclidean three-dimensional space-time in cylindrical coordinates. But this doesn't happen when you have rotation, okay? So when you are in the static case, the integrability is much higher, and you can see that the Newtonian potential u immediately reduced to Laplace equation. And then the remaining function you need to find, which is this gamma, this conformal factor gamma, is given by these two quadratures. So from one of the equations, you get that the derivative of gamma with respect to zeta is given by this product, and the derivative with respect to rho is given by this another. So basically, because u, which is the gravitational potential, is given by a Laplace equation, and we know the entire solution of Laplace equation, we can always find all solutions, because then gamma will be simply given by this quadrature. So up to how difficult it is to perform the integral of these two relationships, gamma is always known, and u as well. Okay, so this is very useful. So basically, the Newtonian potential comes from a linear equation, which is Laplace equation, and then all the nonlinearity implied by Einstein equations is encoded in gamma, but gamma can be always solved in terms of u. But this means that actually static and axisymmetric solutions are known. So what is the solution for u? Well, the solution for u is the solution of Laplace equation, depending on these coordinates, right? So this is how you can expand in multiples. You can use a multipolar expansion to find u, where L is this parameter here that controls that, and that is given by, that is the parameter of this Legendre polynomial. And you have two contributions, which are the contributions that are controlled by AL, that are going to be the asymptotically flat sector of solutions, and those that are controlled by the multiple constant called B sub L, that are going to be those that are not asymptotically flat, and that most probably will induce curvature singularity as infinity, right? Because this grows towards infinity, so usually they place singularities there. So this is basically like in electromagnetism, when you solve Laplace equation in a conductor, and you do it either inside or outside, so you kill one of them because it's going to diverge at the origin, or you kill the other because it's going to diverge outside. So basically, this proposes also a sort of way of constructing solutions, because you can say, okay, because u plays the role of a Newtonian potential, I will consider the Newtonian potential as a given Newtonian source. And then I'm going to solve gamma via the quadratures, and then I'm gonna plug u and gamma on my Weyl metric, and I'm gonna obtain the relativistic counterpart of my solution. As simple as that. So I can say, okay, I will have a point particle, for example. We can say, okay, which is the Newtonian potential of a point particle? Now you will say, well, okay, in coordinates, spherical coordinates is going to be a spherically symmetric potential, right? It's going to be constant over R. Well, I can use U as a constant over R. Let's say that this constant is going to be called magically M. So I'm going to say M over R. I'm going to compute gamma. And from gamma, I'm going to find my entire relativistic version of that spherically symmetric potential. And you might think, or well, I know you know, but initially when you are learning these things, you might think, but this is going to be the Schwarzschild spacetime, right? Because the Schwarzschild seems to be the monopolic field, the monopolic gravitational field, but actually it's not, and it's a solution which is called the Coulson-Chadsey particle, which is an aqueous singularity in the relativistic case, and of which the metric, the entire line element, is not actually spherically symmetric as in Schwarzschild, but is axisymmetric. So basically, when U is what you will call the Newtonian potential of every day, is used on in a Weyl metric, what you get is not Schwarzschild, but you get the Coulson-Chadsey particle. And actually, to get Schwarzschild is much more difficult, and the Newtonian interpretation of the Schwarzschild solution is not a spherically symmetric point-like sort of source, but is a thin rod of mass m and large 2m. When you have this rod of large 2m and mass m, therefore the density is constant, is 1/2. You find using the equations I showed you before that the Newtonian potential is going to be by this expression, gamma is going to be by this other, where you define this in terms of the Weyl coordinates. You plug everything on your bilateral vector one side, and what you get is Schwarzschild in these cylindrical coordinates. So then you move to coordinates at theta, and you get your usual Schwarzschild metric. You see? So actually, although it works very well as a way to find new solutions, the geometric interpretation of what you have in the Newtonian side and in the relativistic one is very different. And another interesting, this is basically Schwarzschild. So if I would solve Schwarzschild in Newtonian term as a problem of electromagnetism, what I will have to do is to consider a thin rod of linear density 1/2 of this form. And what I'm going to get in the relativistic counterpart is going to be Schwarzschild. An interesting metric that is going to be useful on what I'm going to say at the end is this one, which is a simple generalization of the Newtonian case of Schwarzschild. So instead of having a thin rod of constant density, you have a thin rod with some arbitrary density depending on something that we call, or that is called, the deformation parameter. So basically, let us take a thin rod that goes from L to minus L instead of M to minus M, and of mass M, of course. You get that the density is M/2L. I'm going to say that this is going to be delta/2, and delta is this parameter called deformation parameter. And what you get when you integrate Weyl's equations, and you also move to more intuitive coordinates like r theta, what you get is this spacetime. And this spacetime is called the Zipoy-Voorhees spacetime, and it's a generalization of Schwarzschild. Okay, actually, you see that if delta is equal to 1, you recover the Newtonian structure of Schwarzschild, and your metric here actually goes to Schwarzschild, because when this guy is going to 1, this is the Schwarzschild blackening factor, and all of these functions here, they combine in a way that this is the Schwarzschild metric. Why I'm showing you the Zipoy-Voorhees spacetime? Because every time we will be dealing with Einstein equations, Einstein solutions that are addressed with a minimally coupled scalar field, the static limit goes always to a kind of Zipoy-Voorhees spacetime. So that's why we need to know what the Zipoy-Voorhees spacetime is. Some people call it the gamma metric or the Q metric, and is known to introduce this multipolar contribution into the non-killing sector of the metric, which is this function you see here. Okay, so let's deal with solutions. I was telling you about this Weil procedure for a reason, because very soon we are going to realize that there is a very similar situation going on in Einstein-scalar theory, and not with any scalar, but with the minimally coupled one. So many people might be wondering, okay, but why this guy is going to deal with the minimally coupled scalar field if we know there are non-Hertz theorems and so on? So most probably solutions are going to have singularities. Yes, they are going to have singularities. But every time we are dealing with more sophisticated scalar tensor theories, we know that the main, the atom of these theories, like the minimal sector, the minimalistic sector is Einstein with a minimally coupled scalar field, and that from there, via frame transformation, we always can go to other solutions in theories that are more complex. So due to the fact that find solutions in GR is already very difficult, and usually you need solution generation techniques when you want to go to cases with rotation or NUT or exterior backgrounds or whatever. This is already difficult in GR. When you go to modified gravity theories, this is basically impossible, because modified gravity theories, they do not have any of these nice integrability properties of Einstein-Maxwell equations in the stationary axisymmetric circular sector. So you always need to find a way to find solutions there. Usually a static spherically symmetric solution, they can be found. This is sometimes easy, sometimes also anyway very difficult. But fortunately, it is known, and this is going to be related with the Eriş-Gürses theorem I'm going to show you after. It is known that some of the Lie point symmetries of the Einstein-Maxwell theory can apply to Einstein-Maxwell minimally coupled scalar theory. So that's why, in our opinion, it's interesting to understand which are the integrability properties of this system and what we can do here in Einstein with a simple minimally coupled scalar field to eventually understand what is going on in other more sophisticated scalar tensor theories that might be appealing, like, for example, Hordensky or Tost. Okay, so that's why. So we know that actually this Einstein scalar is the essential block to study the most general theory we have with healthy properties in a scalar tensor, which is called Dost, which is the only one that propagates 2 + 1 degrees of freedom and can be made absent of ghosts and so on. And in fact, there is actually one subsector, if you can correct me if I am wrong, 1A that is actually still aligns with the luminical propagation of gravitational waves and all of these cosmological constraints. So I think it's still valid. And it's known that this theory is stable under these formal mappings. What that means, that you can start with traditional scalar tensor theories, which is this dark dot I have here. Let's say that in there you have minimally coupled scalar fields. You can also have a little bit more general scalar field with conformal coupling and so on. Then you have Hordensky theory, which is the next subsector, which are theories, which is the most general scalar tensor theory with second order field equation for both the metric and the scalar. But then you can go beyond and you can ask for higher order field equations while maintaining the healthy propagation of the degrees of freedom. The first sector is called beyond Hordensky, and when you analyze beyond Hordensky, you arrive to Dost. Anything beyond Dost, it will have an extra degree of freedom that is most probably be a ghost and will have Ostrowski instability and so on. And this particular sector of Dost called 1A is stable under this deformal transformation. It's very nice because you can start with Hordensky, and if your conformal factor and your disformal factor depend only on phi, you always close inside Hordensky, so you don't move outside of Hordensky, you move inside theories. So you move in between theories that are inside Hordensky, because this is a change of frame. It's not a Lie point symmetry, so it's not a symmetry of your spectrum of solutions, but it's a transformation that connects two different theories. So when you do this with C phi and D phi, you stay in Hordensky. When you upgrade the form of the disformal factor to depend on the kinetic term of the scalar, the canonical kinetic term, you move to Bion-Hordensky and field equation on third order. And when you also upgrade C now, the conformal factor to depend on X, you go to DOST. So basically, if we know interesting solutions in the minimally coupled sector, or even in the entire sector of traditional scalar tensor theory that also includes conformally coupled scalar theories in which a decent amount of integrability is known as well, via changes of frame, you might be able to construct solutions in these more sophisticated modified gravity theories. That is something we want to do. So, okay, but what do we know about this very simple sector? What do we know about solutions in Einstein gravity supplemented with a minimally coupled scalar field? First of all, we know a no-go restriction, which is the non-Kerr theorem. So we know that the Kerr family has been proven to be unique, the Kerr-Newman family actually, and that this inspired the non-Kerr conjecture that says that black holes in electrovacuum are described only by a restricted set of quantities, which are the mass of the black hole, the angular momentum, and the electromagnetic charges. This implies that it doesn't matter which is the type of matter that produce the black hole via collapse. Any other property besides M, J, and Q are going to be either eaten up by the black hole or radiated away, and the final description of the black hole is going to be given by these three quantities over here. This is valid for these uniqueness theorems are valid under certain conditions, like asymptotic flatness and others. And all of these conditions basically reduce you to the Kerr family Kerr-Newman family from which you extract Kerr, Ryder-Nostrom, Schwarzschild, and all of these geometries. But anyway, we would like to test whether we can find solutions in the minimally coupled sector when you have a minimally coupled scalar. And there was actually solution exist, but because they violate somehow some of the conditions of these non-Kerr theorems, they are usually featuring, at least in the Einstein frame, where you have a minimally coupled scalar field, curvature singularities. So if you want to deal with something that has an horizon and there is a solution to this Einstein scalar theory, you will always have a minimally coupled scalar field. Sorry, you will always have a singularity. What you can do to don't have the singularity is to go beyond the spherical symmetry and somehow be still in a static case with axisymmetry, but your solution will not describe a black hole. But this is you might find, I don't know, maybe a sort of wormhole or a solid or somewhere else, but it's not going to be a black hole. But in any case, this is going to be our starting point, because eventually we would like to use this as a seed on which a change of frame might give us some interesting geometries in other theories. So let us fully scan all the integrability of this sector. So Einstein theory with a minimally coupled scalar field is given by these equations, plus the Klein-Gordon equation. And a solution found by brute force is known since the 60s, which is called the Fisher-Janes-Newman-Winokur solution. And it's a hard to integrate by brute force solution of Einstein equations, which is a slight generalization of Schwarzschild. So basically, this looks pretty much like the Schwarzschild solution, but you see there is this parameter beta, that is a sort of scalar here, and you have this function hitting the two sphere, where the scalar field has this logarithmic profile that actually provides, at the end of the day, a curvature singularity that happens precisely on top of what should be the horizon. So this metric is singular precisely on R equal to M. Anyway, it's interesting that if you take this solution and you apply a frame transformation in which there is no disformal factor, so it's only G mu times C, and C depends only on phi, so you are going to be in the subset of theories with second order field equations, you find something that is actually not entirely pathological like the Fisher-Janes-Newman-Winokur solution. You get something called the BBMB black hole that, via some change of frame that is known as Bekenstein transformation, takes this solution from the minimally coupled sector to the conformally coupled one. And this very precise geometry in the conformal sector has no curvature singularity outside the horizon at all. And actually, it's much healthier, but still the scalar field has some undesired profile close to the horizon, but with no dramatic consequences, I will say. And if you use there a cosmological constant, you completely solve the problem. You find another family of solution called empty zeta family that are completely healthy in that sense. But you need also self-interaction and other stuff. But okay, why we should push for the study of this? Because actually, this model can be studied. It can be studied far beyond spherical symmetry. So, as I show you, as I mentioned before, all the symmetries I show you at the beginning, Ehlers, Harrison, combinations thereof, and etc., they still remain valid when you have a minimally coupled scalar field. So I can construct many solutions, like with NUT, with swirling, with charges, with Melvin, combination, so on, in this system. And I can always try to understand what is going on in a different frame. In the same way, you can move from the Fisher-Janis-Newman-Winokur solution to the BBMB black hole. So this is interesting. And actually, people has been recently working a lot on trying to find solutions with hair and new physics there, etc. So it is appealing. It was appealing for us to try to understand what is going on there. So although the system, although many solutions are known in the minimally coupled sector of Einstein minimally coupled, Einstein with a minimally coupled scalar field, rotation is always very difficult to achieve. Kerr-like rotation. The symmetries I showed you before, they produce NUT, they produce some rotation induced by the interaction of the electromagnetic fields. You also have swirling, but none of this is Kerr-like. Usually to endorse Kerr-like rotation to spacetime is very difficult. You need other solution generation technique, like the inverse scattering technique and others, or the symmetries of some sigma model reduction of Einstein-Maxwell theory, and so on. Nevertheless, there was a solution that was known as the Kerr-Fisher-Janis-Newman-Winokur generalization of the previous one I showed you, and that was given in closed form in a paper by Clement and Gal'tsov, and that is based on a more sophisticated transformation they invented based on the symmetries of some sigma model that arise when you compactify Einstein-Maxwell theory from 4 to 3 on a time-like direction. You apply some symmetries, you go back, and you obtain this very interesting geometry that is basically Kerr with a minimally coupled scalar field around that has this logarithm profile. Okay, so believe that well, this was the only known solution of Einstein minimally coupled scalar field that was rotating if you kill the parameter sigma that is related with the scalar hair. The scalar field disappears, and this solution entirely reduced to Kerr. So it's basically really Kerr modified by the presence of a scalar. So we were wondering, okay, but how is possible that this solution actually exists? Because it's, well, we know these symmetries that I am detailing here are very powerful, and then you can try to construct them. But anyway, it was very, let's say, intriguing the fact that the scalar field always enter in this function h that modifies the non-killing sector of the metric. So somehow when you kill the scalar field, you send h to 1 and you recover Kerr. But all the other functions, f, rotation, and h without a scalar reduced to Kerr in Weiss-Level bedrock coordinates. So there was an indication that the scalar field is somehow only affecting this non-killing sector of the metric. And we were investigating this. I don't know how much time do I have left, because I can maybe speed up and...
Yeah, you should. I mean, yeah, like try to wrap it up. Maybe 5 minutes.
Okay, in 5 I can do it for sure. Yeah. So we realized, okay, look, we have Kerr. This Kerr metric, it seems that the scalar field is only hitting the non-killing sector. And we were like trying to understand why. And this is a simple observation we did, and we realized that actually, if you take a rotating spacetime and you write it in Boyer-Lindquist in Boyer-Lindquist coordinates, and you tune the Boyer-Lindquist answer by putting a new function, an extra function in front of the non-killing sector, actually you can integrate the field equations immediately. And you don't need to go all over this very painful solution generation technique based on sigma models and symmetries of the sigma model that Clement used. And actually, the solution of Gal'tsov, we can integrate in a few steps if you take the metric of Kerr in Boyer-Lindquist coordinates, and you modify Kerr by simply putting a new integration function. You go through the field equations, all the killing equations are going to be satisfied, and you can integrate H from the non-killing components of the Ricci tensor. And this was a very simple observation. Then we proved it in dimension 5. We went to Myers-Perry, and we did for Myers-Perry with both angular momentums completely arbitrary, something impossible to be done actually with the solution generation technique of Gal'tsov that applies when you are in 4-dimensional GR. So what we realized is that actually there was already a theorem explaining why this was happening. And the reason is the following. So the reason can be understood as a scalar extension of what I told you before was called the Weil problem. So Eriş and Gürses showed the following in the 70s, in a basically forgotten paper, that any vacuum solution or electrovacuum, but here I will be dealing only with vacuum, in a Weil-Levis-Papavetru form. So again, you use the nice features of a space-time that is already adapted to stationarity, axisymmetry, and that is circular. So if you take a Weil-Levis-Papavetru space-time that is going to be characterized by a function u that is basically the Newtonian potential, by a rotation, and by a function gamma, which is what hits the non-killing sector of the metric, you can always find an extended solution, but now that is going to be solution to the Einstein-scalar system. So you're going to take Einstein equation with a minimally coupled scalar field that will have the following form. Will have the same Newtonian potential, will have the same angular, the same rotation function, and will have a new function hitting the conformal sector that is going to be given by the previous one, plus a contribution given by the scalar field. Provided that this new function, this new component of phi, gamma phi, and the scalar field you have included in your spacetime satisfying the following equations. And these equations are nothing else than a scalar analogy to the equations I showed you in the Weil problem. Basically, the scalar field will be always given by Laplace equation in a Euclidean 3-dimensional flat spacetime in cylindrical coordinates. And then the scalar field contribution to this function gamma will be always given by these quadratures. So again, the problem is entirely solved because I can always find a solution of Laplace equation for the scalar field in this case, not for the Newtonian potential. And knowing that, I will always find at least up to quadratures the function gamma phi that is going to be here. So I can take any solution, rotated or not, of Einstein theory, and I can construct a new one with a minimally coupled scalar field on top, because rotation and the original gravitational potential do not mess up with the contribution of the scalar field. The scalar field decouples completely, and decouple in the same way the gravitational potential decouples in the Weil problem. And this allows us to construct immediately the solution of Gal'tsov, and it's happening in dimension 5. And you can do whatever you want, because basically you can solve this for the entire multiple expansion. So you can take your Churchill black hole, for example, and put it in the environment of a kind of a scalar background with the entire multiple expansion. You can always do that. You might take Kerr and do the same. Modify Kerr by the entire set of multiple expansions. The one of Gal'tsov is is a particular modification in gamma, because this scalar field has this shape, but this scalar field could be this entire expansion, and you will have the solution. We did the same in dimension 5. I'm going to be very fast here because there's no need. We did it with NUT parameters, with electromagnetic charges, with more general scalar field profile. We may include many things. And we did also in dimension 5 for a Myers-Berry spacetime. So basically, you take Myers-Berry, written in Boyle-Lindquist coordinate, with both angular momentum turned on, A and B. And you can find the rotating solution there, basically, with the scalar field. And all of this is due to the integrability properties of the Einstein-scalar theory on the stationary axisymmetric circular spacetime. And the fact that the 5-dimensional solution we have shown exists implies that there must be an extension of Eriş-Gürses theory in dimension 5, something we are writing now these days. And this is interesting because Weil problem was also analyzed in a paper from M. Paran and Real, I think, in the beginning of the 2000s. So we know there is a well-defined Weil problem in dimension 5, and now we have somehow the scalar counterpart of that. And there is also a later realization of that paper from Paran by Troels, I don't remember the surname, that did the full stationary case. And our solution is proving precisely that in the full stationary case in dimension 5, you can always include the scalar field. When you go to dimensions higher than 5, then some of the conditions that allows you to define circularity in higher dimensions are not fulfilled. Because I think in order to define circularity, you always need d-2 killing vector on your spacetime. And I think at least for metrics like Schwarzschild or Myers-Berry, you arrive up to d-2 in dimension 5, but when you go higher, you don't have it. So then all the scheme doesn't apply. But at least in dimension 5, we'll be able, I think, to find a theory. Okay, so I'm going to close there. I think I am already on the line of the time. Thank you.
Thank you very much. Thank you very much, Adolfo, for the nice talk. Yeah, are there any questions from the audience? Yuta? You want to ask the question, or it was this?
Yes, I pressed the wrong button. Happens sometimes. Sorry.
Yeah, sure.
Hi, Adolfo. I was wondering, did you also look at the black rings?
Yes. Well, I put it here maybe. Yeah, it's the last line. We didn't look at the black ring, but we say that it can be done. Yeah, you can put a minimally coupled scalar field on the black ring as well.
Oh, very nice.
Yeah. But I guess it's going to be much more difficult because of the complexity of the black ring. But I believe you can find the exact solution with the scalar. Especially if you can work in Weiss level by Petru coordinates.
And I have a second question which concerns, I mean, the scalar. Does it matter whether you have an ordinary scalar or a phantom scalar?
I think that the phantom do not spoil the construction, but definitely if it's not real. So for example, with complex scalar, then I think the Eriş-Gürses theorems breaks down. But if you change the sign of the kinetic term, I would say it works. Although we didn't try.
Okay, thank you.
Thanks to you.
There's a question in the chat by Jayu saying most of the solutions here with scalar here are naked singularities. Are there any treatments in the solution generating method can preserve the horizon?
So when you are in the minimally coupled sector, you will deal with these singularities because it's basically what the non-Hertz theorem is telling you. The way to deal with them is to use changes of frame. So now you find solutions within the same theory, like you start with a very basic Fisher-Newman-Winnicke and you make it NUT, for example, via an LS transformation. You are still in the minimally coupled sector. But if you move to the conformal frame, that solution is known as well, and it's known to be regular there. Of course, there are subtleties with the presence or not of the cosmological constant, but at least they are not going to be naked singularities. And this is mostly achieved via the change of frame in the concept of Einstein-scalar. In the concept of pure GR, well, it depends how complex is your configuration. You might have curvature singularities as well. But usually you can describe very nice vacuum solutions that are well known to have an horizon and that are okay. Yeah.
Good. Yeah, other questions?
I didn't see the chat, sorry.
Sure. Yeah, I wanted to ask, what happens? You mentioned it briefly now, but yeah, this is all asymptotically flat, right? So what happens if you have a cosmological horizon?
Yeah, you have the thing is that when I showed you before the Weil problem, which is the very basic setup you can use here, I already put it inside cosmological constant or even Maxwell field, spoils the Laplace equation structure for the Newtonian potential. So it's very difficult. So if you have lambda turned on, no matter the sign, you will have an issue with the integrability, and you don't have a Laplace equation that allows you to completely determine the system, with or without rotation. What might be doable, but I'm not sure because there are a few papers only on that, and I'm never sure if they work or not. I never try. Is that usually what you can do is to preserve some integrability properties when you have a perfect fluid. So there are people that study these Lippoin symmetries under the presence of a fluid, and you can always dress your cosmological constant in terms of a fluid, and then try to apply these techniques. But I don't know if it works, to be honest.
I see. Actually, yeah, a couple of years ago, we wrote a paper on Brans-Dicke theory, non-minimally coupled Brans-Dicke theory with a cosmological constant, and we showed that, I mean, there are no non-trivial configurations for phi. So phi has to be either a constant or omega has to be like towards infinity in order to be like GR. So, but I don't know what happens if you go to the conformal frame. So that would be interesting to check actually. Yeah, anyway, Yuda, do you raise your hand? And there are a couple of questions in the chat.
I forgot another question. Eugen is also here with me, Eugen Radu. So the natural question is actually, can you also generalize to a complex scalar field?
Yes, this we know at least at the level of the Eriş-Gürses theorem doesn't work, because the phase of your complex scalar is gonna spoil the Laplace equation, unfortunately. So in very generic terms, this cannot be done. But we were looking at this with my colleague, with Mokhtar Hassan, and there might be a way out, or maybe you will need to fix the phase of your scalar in a very peculiar way. But it's not clear that you will have the same level of integrability like in Eriş-Gürses when this is real. So I would say being complex will spoil, it will destroy the integrability. That would be my first answer.
Yeah, that's a pity, because it would be really nice to have these black holes, curved black holes with scalar hair in a not only numerical, but in a closed form. Yeah, thank you.
No, it's an interesting application. Yeah, it's true. But look, I don't have a definite answer, so it's something that must be explored. My intuition is telling me when I saw it, at least some time ago, that the phase will destroy the applicability of the theorem. But I might be wrong, so I'm not going to be 100% definitely.
Okay. Yeah. Thank you.
Thanks to you.
There's a question in the chat by Eloise.
Yes.
If you go beyond the circular symmetry, how would the Ernst formalism fail? Or could it be extended to non-circular spacetimes?
I would say it would fail because the fact that you can write the Einstein equations in terms of these complex potential depends a lot on the metric you have. You see, so the symmetries, I agree, the symmetries are stationarity and axisymmetry. Okay, so circularity is not a symmetry, so shouldn't particularly exclude completely the possibility of having a formalist like this one. But then when you are taking the field equations written in metric form and you want to achieve the form of these field equations in the Ernst scheme, then the fact that this is circular allows you to find these twist equations that I wrote there. And I think this is going to be the main problem if you try to generalize this to non-circular spacetimes. But to be 100% honest, I don't have a definite argument to tell you why it doesn't work, why it shouldn't work. But I know it's going to be very complex to do this because I'm not sure if this twist equation might exist, but definitely that is something that should be explored. For example, when you go to higher dimensions, you have arguments to say why it doesn't work. Because if you go from dimension 6 on, you will have an issue with the number of killing vectors you have. And also when you have cosmological constant, it's completely spoiled. But with non-circularity, I will say the main problem is related with how to define this complex potential and make everything. The thing is that, yeah, I think I have an argument. So when you write down things in Ernst, or when you have this Weil problem, what is happening is that your metric is block diagonal somehow, right? So you separate your entire spacetime in two blocks, one with the killing and one with the non-killing. Although if there is rotation, there are cross terms in your block on the killing sector. And this block diagonality basically is what allows you to project your field equations in this three-dimensional spacetime with cylindrical symmetry. So I will expect that by not having this block diagonal form of your metric, which is given by circularity, you won't be able to project in this three-dimensional cylindrical spacetime. That will be the wall I see when dealing with non-circular spacetimes. But I'm not sure if someone proved it. So,
yeah.
But it's an interesting question.
Thanks a lot. Yeah, if there are no other urgent questions, since we already exceeded like an hour and a half, I would suggest.
Sorry, man. I told you
No,
stop.
it's fine.
Because
It was really interesting. Let me stop the recording.